Hi, welcome back to the first law of thermodynamics and physical chemistry. My name is Kevin Tokoph. Make sure to like the video and subscribe to the channel for future videos and notifications. It's very much appreciated. In this video, we're going to go over an extremely important topic that's often introduced in the first or second chapter of physical chemistry, and that's the concept of heat, and arguably one of the most misused terms in the English language. Okay. I grew up in Texas. All right, my entire life so far has been in Texas. Okay, and you'll often hear the following phrase, something like, "The Texas heat is terrible." Well, when somebody says that, they're often referring to the temperature. That's what the reference is to. All right. My father-in-law and mother-in-law, they are from Arizona. Okay, Arizona is probably, honestly, hotter than Texas in the summer. Okay, just because it's dry heat. But again, dry heat is another misuse of the term. You know, Arizona heat, New Mexico heat, whatever. Okay, it's a misused term. Why? Because heat does not explicitly describe temperature. It describes an energy transfer. Okay, so when you talk about, say, the Texas heat out, right, the temperature really isn't changing. I mean, if you're looking at just a point in time, the temperature doesn't change if you're just looking at a single instance in time, right? But people refer to the heat at that moment in time. Now, heat is something that describes an energy transfer, and specifically it's thermal energy transfer. Okay, so what is thermal energy? Well, thermal energy is any kind of energy that causes a change in the motion of molecules. So here's an example. I have a container here with a gas, okay? And let's suppose that heat, the energy transfer, is causing energy in the form of thermal energy to be transferred into the container. Well, I think we have an intuition. You know, if you were to take a can of soda, right, and say, assuming it's cold, you got it out of the fridge, and you put it in the microwave and turn the microwave on, right, to high, I think we have an intuition that energy transfer is going to occur such that the energy is transferred into the can of soda. Sorry, my cats are running around all the place. Anyway, so energy is going to be transferred into the can, and what's going to happen to the fluid in the can? It's going to increase in temperature. The same, and this doesn't just apply to gases. This applies also to liquids and solids, right? If there's a difference in temperature between 2 points, right, then energy transfer will occur to put them in equilibrium. All right. So we have this intuition, like, right? If you go, just anywhere, room temperature, right, and you have a can of soda that's cold initially, if you just let it sit for a few hours and you come back, it's gone to room temperature because energy was transferred ultimately from the room into the can, such that the can increased in temperature. And we really don't say the room decreased in temperature just because of air conditioning, but essentially energy had to be transferred from the room into the can. And that's what heat describes. So here's the idea, okay? If you put the energy due to heat into a system, the temperature goes up, right? Likewise, okay, if I were to remove energy in the form of thermal energy from this canister, then the temperature should go down. So in other words, if I remove heat, so heat leaves the system, then I should have a temperature that drops, at least the temperature in here, right? So that follows from the principle that if I have the derivative of the heat with respect to the temperature, that's going to equal the heat capacity, okay? So what is heat capacity? Heat capacity is essentially, from a very understandable way, it's the ability of a substance to resist changes in temperature. Okay, so what does it mean? Well, think about it like this. If I apply a lot of heat into a system, right, and the temperature doesn't change a whole lot, right? In other words, I can sort of think about it this way, okay? If I have my heat capacity, N is the number of moles, but this is the heat capacity, and I essentially look at the heat, Q, over delta T. Well, let's suppose I apply the heat, right? A lot of heat, so a lot of heat, high amount of heat, okay, so lots of energy transfer, but the temperature doesn't change a lot, it's low. Well, then if the temperature doesn't change a lot, okay, so low temperature change versus high amount of heat, then I'm taking a number and dividing by a very small number, which means the heat capacity should be high, right? So in other words, what I'm saying is if you apply some amount of heat and the temperature of the substance doesn't change a whole lot, then that substance has a high heat capacity. On the other hand, if you put the same amount of heat in and the temperature changes drastically, then it has a low heat capacity, because then you'd have something in the denominator that would also be high, and then you'd have a lower heat capacity. That's why it's the ability of a substance to resist changes in temperature. Okay. Now, here's another key here that I want to sort of go into before we get into the mechanics of heat and heat capacity. Okay. I think we have this intuition. If I'm putting thermal energy into a system, the system can't drop in temperature, right? Assuming I'm only adding heat, no change in volume or anything. If I'm putting in thermal energy, the temperature can't decrease, right? So that means that if dq is positive, then dt also has to be positive, okay? But if I take thermal energy out, then the system's losing energy. It has to drop in temperature, so the opposite also follows. If dq is less than 0, then dt also has to be less than 0. So essentially what you have here is, for heat capacity, you have either a positive number divided by a positive number, or a negative number divided by a negative number, which means that heat capacity is always positive. You can never have a negative heat capacity. That's one trick question professors like to put on exams. You have a negative heat capacity. Does it make physical sense? Well, no, because of the definition, and the definition ultimately comes from dq over dt. This derivative right here has to equal the heat capacity times the number of moles, essentially. Okay? Heat capacity, always positive. Another way of saying it is it can never be negative, and also it can never be 0, but we normally don't include that. Okay? Always positive. All right? And that's basically the basics of heat capacity. Okay? If you put thermal energy into a system, it has to go up in temperature. And the amount that it goes up in temperature is determined by the heat capacity. Okay? Now, heat capacity itself over a small range in temperature. So maybe you go up 1 degree Kelvin, 2 degrees Kelvin, okay, maybe, okay. All right. Over that short range of temperatures, heat capacity is essentially a constant, okay? But in reality, heat capacity is a function of temperature. That's what I'm indicating right here. Heat capacity is a function of temperature. So technically, when you're writing heat capacity, if you were to write it using the formal definition, you would say that the derivative of heat with respect to temperature is equal to the number of moles times the heat capacity as a function of temperature. And this is actually a formal way to write it, okay? Now, what I can do here, and I'll do it right now, is if I multiply both sides here by dt, so the dt here cancels, then I get this form of the equation, okay? And I'm going to put the n right there, is that dq is equal to n times heat capacity as a function of temperature times dt. Then what I can do is I can integrate both sides. This is an inexact differential that we'll mention those in another video, but this is essentially just q, okay? Not delta q, it's just q. And then this is equal to n times the heat capacity as a function of temperature, okay, times dt integrated from T1 to T2. So this right here, this is the formal definition of heat. Okay, if you get it into the integral form, not the derivative form. It's q is equal to n times c dt. C can be a function of t, integrated from T1 to T2. All right? Now, the question is, how do I deal with heat capacity if it's a constant versus if it's a function of temperature? Well, the nice thing is this is an integral, and hopefully you know how to deal with integrating functions. All right? Let's actually look at it just so you can get some practice with it. Suppose in this first example, C is a constant over T1 to T2. And this would be for very small changes in temperature. Okay, so maybe if you're going from like 300 Kelvin to 302 Kelvin. So maybe usually a max of 4 Kelvin is maybe what you would do. There's no set cutoff, but if you start to get massive changes in temperature, there's a lot of error. But over small ranges, you can assume it's constant. Okay? All right, so I have n times the integral of c dt from T1 to T2. The heat capacity is a constant, right? So I can pull that outside the integral and get nc times the integral of dt from t1 to t2. This right here, okay, this whole thing is just delta t. And delta t is just t2 minus t1, right? So that makes that easy. If you know the temperature change, just multiply the heat capacity times the change in temperature, delta T. However, it becomes a lot more complicated if you have a function for heat capacity. And a lot of times in your chemistry textbook, they'll have tables of this tabulated in the back. There's different functions for different types of gases. So now suppose the heat capacity is given by this function of temperature. A, which is a constant, in fact, A, B, and C here. This is not the heat capacity. This is just the lowercase c. These are constants. So it's A plus BT plus constant C times T squared. That's your function for heat capacity. And A, B, and C can be different numbers depending on the gas. Okay? So you're still going to have the same general formula. The heat is equal to N, the number of moles, times C as a function of T, times dt, integrated from T1 to T2. However, because I know what C, the heat capacity, is as a function of temperature, I can just take that and plug it in right there for C as a function of T. And that's what I get this. I have this now in the integral, A plus BT plus CT squared, and then I'm going to integrate over T. Okay? So what I can do is I can actually break up this sum into a sum of integrals. Remember, you have this rule from integration. The integral of a sum is equal to the sum of the integrals. So that means I'm going to pull the n out and just multiply by all of this. Integral of a dt from t1 to t2 plus b times integral of t dt from t1 to t2 plus c times integral of t squared dt from t1 to t2. And now these are just simple power rule integrals. So when I do this, I'm going to get the heat is equal to n times all of this. A times integral of t is t, evaluated from t1 to t2. If I integrate t to the first power, that's going to be t squared over 2 times b, evaluated from t1 to t2. If I integrate t squared dt, that's going to be t cubed over 3 times this constant c, evaluated from t1 to t2. And I'm just going to evaluate that integral, and then that's going to be my heat. Okay? And that's how you would calculate that. Right? Now, there's one more caveat here for heat, the basics, and then we're going to do another video on heat after this. Okay? There's actually several kinds of heat capacities. So I've indicated here, we've just talked about heat capacity as a function of temperature. Okay? However, under different conditions, you can have different forms of the heat capacity. And this is where we're going to introduce different types of processes, and there's two in particular. One of the types of processes is called isochoric, and the other one is called isobaric. Okay? What do these things imply? Well, if you have an isochoric, that one's a little less intuitive. Isochoric means there's no change in volume, meaning that the volume is constant, or delta V is 0. If you have an isobaric process, remember bar is sort of an indicator of pressure. So if it's isobaric, that means there's no change in pressure. Pressure is constant. Okay? If you're talking about the heat capacity for an isochoric process, you still have this heat capacity C. And then normally if it's constant volume, you stick the subscript of a V out in front of the C. Okay? Normally in physical chemistry, whenever you have a variable or a function, okay, in this case heat capacity could be a function, but you're holding a variable constant, you normally stick that variable out in the front as a subscript, and that indicates that that variable is constant. Okay, so if you were talking about, say, the heat at constant volume, you'd stick a heat out here and just stick a subscript of a V there. That indicates that you're at constant volume. Okay, if you're isobaric, that means that the pressure is constant. So you still have a heat capacity, but you'd indicate a P there to show that it's constant pressure. Likewise, the heat itself is Q at constant pressure with a P subscript there. Now, normally when you look at how most textbooks begin to write heat and heat capacity and so forth, they normally put at first you have this C as a function of temperature times dt. But almost always, after a while, you start to drop the C as a function of temperature because it's just implied. Anyone who's looking at physical chemistry information knows that heat capacity is a function of temperature. Okay, so normally you could write, in theory, C as a function of T at constant volume and C as a function of T at constant pressure, but nobody does that just because it takes up a lot of space. They just write C sub V for heat capacity at constant volume and the same thing for pressure over here. Okay, and there are going to be cases where we look at specific problems and the thermodynamic process could be isochoric, right? How do you deal with that? Well, you'd have to use the heat capacity at constant volume. There are other cases where the heat capacity could be at constant pressure. The process is at constant pressure, so you'd have to use Cp here. Okay, in the next video, we're actually going to look at the relationship between Cp and Cv. Thanks for watching. Hope this video gave you an idea about heat and heat capacity. Make sure to like the video, subscribe to the channel for future videos and notifications. Thank you. Hope it helped.